So welcome back. Today we're going to talk a bit about angular momentum. Now angular momentum L is equal to the rotational inertia I times the angular velocity omega. This is very akin to linear momentum P, which equals the translational inertia times the linear translational velocity. If we look at Newton's second law, for translational motion, the force net equals the change in momentum divided by the change in time, which also equals mass times acceleration. If we go ahead and look at the rotational version of Newton's second law, our net torque is going to equal our angular momentum, the change in angular momentum, divided by the change in time, which is equal to the rotational inertia I times the angular acceleration. So for conservation of angular momentum, let's look at that torque, the total torque, equal to the change in momentum divided by the change in time. We can rearrange this a little bit to be the change in angular momentum equals the change in net torque times the change in time. If our net torque equals 0, then the change in angular momentum also must equal 0. So what is the change in angular momentum? It's just like all the other changes. We have the angular momentum after minus the angular momentum before, which equals 0, which means they are equal to each other, which means angular momentum is conserved. So the law of conservation of angular momentum, if there is no net torque acting on an object, then the angular momentum of that object remains constant. And this is very comparable to the conservation of linear momentum. If there is no net force acting on an object, then the linear momentum of the object is constant. So just like other angular quantities, angular momentum is also a vector quantity. The vector points along the axis of rotation, and you can find this vector using the right-hand rule. So let's go ahead and do a problem. In this problem, we have a figure skater rotating at a constant angular velocity of 6 radians per second, with her arms outstretched at a radius of 0.7 meters. If she brings her arms into a radius of 0.4 meters, what is her angular velocity? Now we can approximate the skater as a solid cylinder with mass of about 80 kilos. So first, solid cylinder, the rotational inertia for that would be 1/2 mr squared. Our conservation of rotational momentum says before is the same as after. And if we write that out, our rotational inertia times our velocity before equals rotational inertia times velocity after. If we solve for the rotational velocity afterwards, and then go ahead and plug in what we know to be true for the rotational inertia. Now these are both cylinders. The only difference is the radius. So the 1/2 m gets canceled on either side. What we're left with is a radius before squared times our initial velocity divided by the radius final squared. And what we end up with is a final velocity of approximately 18 radians per second. So she started off with an initial angular velocity of roughly 1 revolution per second, and she ended up with an angular velocity of roughly 3 revolutions per second. So that's it for this video. Thank you for watching, and remember to check As You Learn for the rest of tonight's assignment.